to stage transfer. You also need to implement a state machine to keep track of what stage you're in.
I'll be going to a breakout room. Is that all right?
Yep, sure. Okay, so here's something else I did in yesterday's session. I'm going to ask for someone to volunteer and draw a block diagram of what they think part 3 should be implemented as. So not the exact solution, but just a general overview of what it should look like. Does anyone want to step up? So what you can do is share your whiteboard and then just draw something. Does anyone want to have a go at that? Okay, Kieran. Yeah, you should be able to share your whiteboard.
Give me a sec. So it's a block diagram of the, so does this have to include like the, like your NEOS? Can you see my screen?
Yes, we can see it.
So like the FPGA and then NEOS, are the sort of, would it be similar to the block diagram from
so you can go,
manual?
Yeah, you can do it at that detail, or if you want, you can just show the lines coming from the bus lines coming from the NEOS processor from that point onwards. It's up to you.
And then you have, so what would be, be like,
that's a cool tool, by the way. What are you using?
oh, this is the Microsoft Whiteboard thing. You know,
Right.
you click on the bottom right of your screen where the Windows Ink workspace,
Yes, I see it.
and then tap on Whiteboard, depending on what build you have of Windows 10.
Okay,
you've got-
I can't see whiteboard. I can see Sketchpad, Screen Sketch.
Okay, so you've got one of the older builds of Windows 10.
Yeah.
On the newer builds, probably for the last year or so, they've changed that thing to now have Whiteboard. So
Okay, cool. I'll check it out
But-
later. Thanks.
yeah, but yeah, I think you can do the same thing in OneNote, very similar. But yeah.
Oh, I don't have that. Up to date.
Yeah, I'm probably on the newest build. That's probably why. Avalon switch fabric, and then you have and then yeah, this would be I want to do that. And then over here you also have does that look about right?
Yep, so that looks good for the overall block diagram. Now, what I guess we're looking for is more detail about the section in between external bus and the two slave devices. So what comes out of the external bus, and then how does it sort of split from there, or not in terms of code, but like just in terms of the lines, I guess.
Oh, like the right. So like the whatever the address lines are and stuff. Okay, yeah. I see what you mean. Okay, so if we draw, so you have at a quartus.
So maybe not that much detail. Okay, so if you think about the bus, you have signals like bus enable, right? Write data, address, those kinds of things. So some of those signals are going to need to be split to go to the two devices. Some will just be copied to both. So maybe focus on the ones that need to be split. So which of those bus lines?
These two, pretty much.
Mm-hmm. And there will be some coming back as well that will need some kind of logic to sort of switch between signals.
I suppose so. Right, because you can't have both the reading and writing can't be.
Go through these two to begin with.
Okay, so we'll start off with bus enable, and then it sort of goes into like.
Don't go into the logic, just sort of the line. Okay, so let's start with bus enable. So there's only one bus enable signal that comes out of the external bus.
And then it sort of gets split off.
Right. So if you split it, if you just send it to both, what is the issue with doing that?
And both get enabled at the same time.
Exactly. So you don't want to do that. So there would need to be some kind of switch in between there, right?
Yes.
Okay. So you can draw that in like a logic switch if you want. Yep.
And then the address will also go to. It's just getting messy.
Yeah. To both. Yeah. So that address lines that go to both might be some or part of the actual 20 address lines that come out of the external bus.
Yeah.
Okay, now from each of the slaves, you will get a returning acknowledge and a read data, but the external bus can only take one read data signal and one acknowledge. So that also needs to be split on the way back from those, or merged, I guess.
I think it's a different color. And something like that.
Yep, that's exactly correct. So, yeah, maybe I should have recorded that. You did a good job. Thanks for that.
I can send the image or something if you want.
Yeah, that would be good too. So that explains what you need to do for part 3 as a block diagram. So everyone just needs to write the equivalent in the Verilog.
Oops. Okay,
Aaron,
maybe.
thanks for that, Karen. Aaron,
Yeah, no worries.
do you want me to go in the breakout room or?
I can take it.
Okay. Okay, so are there any questions about what Kieran went through? Was there anything that was unclear? Is the address 0 always 0? Yes, if you are, well, yeah. Because we're using a 16-bit data bus, then, and because all the half words in the memory space are half word aligned, that means each half word will start at a multiple of 2. So yes, the address bit 0 will always be 0. If we were using a 32-bit bus, which we'll be doing for lab 2, then it would be word aligned, which means that the bottom 2 bits would always be 0. Does that make sense? Okay, cool. Any other questions? Okay, here's one. Can you explain again how... Oh wait, sorry, this is a private question. Okay, so I think this is worth telling everyone. So the question is, can you explain again how the 2 bits become 0? So I'm guessing other people are also still unsure of that. Maybe I should share my screen and go through that one. Okay. So if we're going through addresses in memory, because when we have a 16-bit bus, therefore we are addressing half words in memory. So each half word is going to be aligned to multiples of 2. So the first half word will start at 0, and the second be at 2, because each are going to take up 2 bytes. So this would make up the byte at address 0 and the byte at address 1. And then the next one obviously would take up 2 and 3. So the third starts at 4. Okay, so if you were to write these addresses here as binary, you would have just the bottom 4 bits would be zeros, 2 would be like that, and 4 would be like this. So you notice that this bit here isn't changing, it's always 0. And to access the, oops, what did I just do? If you needed to access an odd address where the address byte has a 1 in the last bit, that would be done through the byte enable bits. So the byte enable bit 0 would then equal 1 in that case, but the address is still aligned to a multiple of 2. If you had a 32-bit bus, I'll just draw it in a different color. Okay, so for 32-bit bus, you would have words. So the first word would be starting at address 0, and it would contain bytes 0, 1, 2, 3. The second word would be starting at 4, and then 8, and so on and so forth. So if you were to write these as binary, and the next one would be 1100. So what you'd notice here is that the bottom 2 bits don't change. And if you wanted to go to any of the intermediate bytes within that, which would be the sub-bytes of the word, then you would use the corresponding byte enable bits. So now there would be 4 byte enable bits. So if we wanted to access this particular byte here, your byte enable bits would be 0, 1, 0, 0. If you wanted to access these 2 here, then your byte enable bits would be 0, 0, 1, 1. Did that answer your question, the person who asked? Oh, okay. Seems like they lost connection during that explanation. Maybe I'll talk to you individually later on instead of going through it again. Did everyone else understand that though? Maybe I should ask, did anyone not understand what I just explained? Okay. The 32-bit part again, okay. Which is pretty much what the original person asked. So let's go through that again then. Okay, so I was talking about for a 32-bit, for a 32-bit bus, your memory is word aligned. So that means that if you are accessing a particular byte, it will be part of a word that is aligned to multiples of 4. So your first word in memory is going to be starting at address 0. Okay? And if you were to look at that word in memory, or if you were to look at the bytes of that word, the first byte would be starting at address 0. The second byte would be address 1, 2, and 3 in memory. Okay, the second word will start from the next address after this, which is going to be address 4. Okay, and that word will be made up of the bytes 4, 5, 6, and 7. And then the third word is going to start at address 8. And then the next word will start at address 12. And that's how it will go on through memory. So the address lines that come out of the NEOS processor are going to only show the word that that particular address that you're trying to access is part of. So it will show where the words start. So 0 in binary is just zeros. 4 is going to be 0, 1, 0, 0. 8 will be 1, 0, 0. So you can see that there's a pattern happening here where the only bits that are changing are everything above these 2 bits. So that is why these 2 bits always stay 0, because multiples of 4 would mean that the 2 lower bits are always 0. If you wanted to access an intermediate byte, so let's say you wanted to access this one here. So that would mean that the address lines would show the address of the start of the word that it's part of, which will be 4. And your byte enable will equal 0, 0, 1, 0. And that is equal to 2. In binary, 0, 0, 1, 0. Okay, so that's how you would access an intermediate byte. Or if it was an intermediate half word, it would be 1, 1. And this address value would still be the same. Do I have any follow-up questions now? To the original person that asked the question, does that make sense now as well? Okay, cool. So if you are writing to address 4, you would also need to specify what you are trying to write. Are you trying to write a half word? So that means 2 byte-enable bits will be on. Are you trying to write a byte, which means only one of those byte-enable bits will be on? Or are you trying to write a whole word? That means all 4 bits would be on. Does that make sense?
If we're trying to write a 32-bit word onto a 16-bit bus, does it automatically figure out that it needs to do 2 transactions?
No, it does not. So that is where for example, for lab 2, where you have the 32-bit bus coming from NEOS and your SRAM chip is 16 bits, your SRAM controller logic is what does the conversion or translation. So it will need to keep track of its own state. So there would be 2 states in this case, where the first state is transferring the lower half and the second state would be transferring the upper half. So the logic within that controller module will be the thing that does it. Does that make sense?
Yeah.
Okay, cool. So there's another question for half word address. So sorry, MD, can you please elaborate on your question? I'm a bit unsure what you're trying to ask. Yeah, if you're doing a half word transfer, the address would still be 4. I think what you're asking is, yeah, so the multiples that you go by would depend on what the data size is, the data bus size is, or the bus size. If you have a 16-bit bus, as in lab 1, then everything is half-word aligned. You'll be accessing some half-word out of all the possible half-words in memory. And each of those half-words will be at multiples of 2. For a 32-bit bus, which is in lab 2, you are accessing some or all of any word that's in memory. And all the words in memory are aligned so that they will all start at some multiple of 4. So if you are accessing a subset of the word, then the address that is given on the bus would still be the start of that particular word. And the byte enable will specify what subset it is. Not sure if that answers your question. Yes, the syntax should be case sensitive. So if you define a wire that is called some wire, if you have a capital S, then you have to use a capital S wherever you use that wire name. Okay, so Yifan has asked, is the ACK set high at the beginning of the transaction? No. If your transaction takes more than one clock cycle, it would only be set high in the final clock cycle. So what you'll find in Lab 2, it takes 2 clock cycles to complete the transfer. So the acknowledge should only be set high in the second clock cycle, during the second clock cycle of the whole transaction. There's another question, why would you only put comma in the module section? I'm not actually sure what you refer to there, MD. You might need to explain in a little more detail. Maybe paste a little bit of code that refers to what you're talking about. Emily, yes, I'll put you into a breakout room as soon as Aaron's done. I think he's in a breakout room at the moment. Okay, no worries. MD, just to reiterate, I think if you're referring to the module declaration, then maybe include some code like this. Oh, okay, are you sharing your screen? Okay, do you mean why are you putting, feel free to talk, by the way, if it's easier to explain through the mic. Are you asking why there are just comma separated names here?
It should be like not comma, right?
No, it is. So in the module declaration at the top, you are meant to include a comma separated list of all the inputs and outputs that you are going to have to that module. So these are the list of port names that the module should have. And then subsequently, just after this section, you should specify whether those port names refer to inputs or outputs or bidirectional.
So in module, we should always put comma inside the module.
Yeah.
When we declare port, we use the semicolon.
Yeah, a semicolon will denote the end of a line of code. So that's why if you see at the end of this comma separated list, there is a semicolon.
Yeah.
So that module declaration is just one line. It's just been put onto multiple lines just for the sake of readability.
And
yeah, and then each of the declarations that say whether it's an input or output is one statement line as well. That's why you need a semicolon.
And in SM controller, like these one logical not, right?
Yeah, the ones with the underscore n, they mean active low. That means a value of 0 on those particular lines activates that function.
This one is inverter.
Yeah.
So inverter means like it invert one.
Are you showing me something? I can only see your snipping tool window.
I'm showing you my screen.
Oh, I can only see your snipping tool window.
Okay, I'm sharing the screen.
Please don't show me the screen if you have your answers there, though. Unless it's for part 2, which should already be done.
It's part 2.
Yeah.
Can you see now?
Yeah.
So this one is inverter.
Yeah, so the tilde is a bitwise inversion. In this case, the thing we're inverting is just 1 bit, so it will just act as a NOT gate.
So 1 bit it inverts to 0.
Yes, correct. If it's a 1, it goes to 0. If it's a 0, it goes to 1. But if it was multiple bits, each separate bit would be inverted.
Okay. And what about this logical NOT?
It does a similar thing for a 1-bit signal. For a multi-bit signal, it will actually just say, is this value not true? So true would be anything that's not the value 0. If it
we can put also inverter there.
Yeah, you could put a tilde there if you wanted to. Yeah.
Okay, thanks.
That's right. The SRAM chip, on the other hand, each address is 16 bits wide. Okay?
Yeah.
And you can say that they're subsequently made up of 2 bytes within those 16 bits. So if on the process end you want to access address 5 or byte 5,
yeah,
the processor will say, I want to access address, in the case of a 16-bit data bus, it will say, I want to access address 4, and the byte enable is going to equal 1, 0. Yeah?
Yeah.
Following? Because it's an odd address. Now, this byte here maps to this section here. Yeah? Because this would be byte 0, 1, 2, 3,
4, 5,
4,
yeah.
and so that would be 5.
Yeah.
So on the SRAM chip end, this address needs to become this address. Yeah? And the byte enable bits will become
0, 1.
Your upper byte would equal 0, and your lower byte would equal 1, to say that this byte is activated.
Yeah.
Okay, so that conversion here is actually a division of 2.
So first of all, the processor want to access address 5, right?
Yes, the byte 5 in its byte addressed memory. Yeah.
Yeah. Then you mentioned the address equals to 4. That one not clear.
Because byte 5 is part of the half word that starts at address 4.
Oh,
Okay, because you have a 16-bit data bus, so you are half word aligned in memory.
okay. So we are actually doing conversion.
No, this part here is done by the processor. You're not doing that. You're doing the conversion from that to this in your SRAM controller.
Okay.